So here is another example of related rates. Example about falling ladder. So here is the idea. There is a certain wall, let's say wall of a building, and then there is a ladder that is leaning against this wall like this. Let's say this is my ladder. Leaning against the wall. And now, let's say that this ladder starts moving. For whatever reason, it doesn't stay still anymore, it moves down, it slides down. So ladder is sliding down. So what does it mean? It means that the top point of the ladder actually moves down. So let me draw it with different colors. So this point moves down like this. Now the point that sits on the ground, this point, actually moves away from the wall. So it moves like this. And altogether the ladder becomes, it's actually falling down, so it becomes more flat. So the new position of the ladder might be something like this, maybe. And then further down, it may also become like this. So this is what we call falling ladder. So it doesn't fall all the way down, but it moves down that way. Now what's given? Given that the bottom point of the ladder moves away from the wall at a speed of 1 foot per minute. So let me write this down. So, one more thing. The total length of the ladder is 10 feet. 10 feet ladder. Now the bottom point of the ladder is moving away from the building at a constant speed. At the speed of 1 foot per minute. So this speed here is 1 foot per minute. And now the question is, how fast does the top point of the ladder move down? It does move down because the ladder is sliding down. And here is the question, how fast is the top point of the ladder, this point, moving down or sliding down? At the moment when the bottom point is 6 feet away from the wall. Question mark. So here's what this problem is about. It's given that this distance from the bottom point of the ladder to the wall, so this distance here, maybe I'll just pick the color, so this distance here is 6 feet. The length of the ladder is 10 feet. Now, actually, since the ladder is moving, so we're talking about one single moment of time. Because before that, the ladder was actually closer to the wall, and so this distance was smaller than 6 feet. Now, as it starts sliding down, so the bottom point moves away. At a certain moment of time, it will be exactly 6 feet, and further, it will be, and after that, it will be further away. So, it was only one specific moment of time when this distance was exactly 6 feet. And the question is, at that very moment of time, what was the speed at which the bottom point is moving down? So this speed is the unknown speed. So this speed is unknown. This speed is given, it's 1 foot per minute. Once again, this problem, like the previous example, this problem also, this example describes dynamics. So there is something moving, so it wasn't about ball, but it's about ladder still moving. So calculus is all about movement, about dynamics. And once again, in order to solve this problem properly, we need again to follow the same procedure like before. Step 1 would be to determine the two quantities. So I guess I need to erase this text. So step 1 is step 1, the two quantities. Now, in this example, those two quantities are actually more tricky to determine. In the previous example about inflating ball, the two quantities were seen clearly on the picture, like radius and volume of the ball. Here they are less clear. So let's go again with the two quantities. So first should be the quantity whose rate of change is unknown. And the second should be the quantity whose rate of change is known or given. Now, what exactly is unknown? The unknown part is what they asked us to find, is how fast this point moves down, how fast the top point of the ladder is sliding down. But what is the quantity that changes at this rate? Which means this speed of movement of this point represents rate of change of which quantity? And it's a little bit tricky, but if you think of it, it represents the following quantity. It represents the height of the top point of the ladder, so that's height. And as the top point moves down, so its height will decrease, and if the point moves down at a certain rate or speed, so the height will decrease at that very rate. So the first quantity, the quantity whose rate is changing, whose rate of change is unknown and exactly asked for in the problem, that quantity is precisely height of the top point of the ladder. So it's height, and height is typically denoted by h. And once again, the speed at which or rate at which this point moves down, it's exactly the rate of change of height, and that's exactly the derivative, which is h prime, and this is the unknown. Now the quantity whose rate of change is known, what is known? Known is the speed of 1 foot per minute. It's the speed at which this point moves away from the building. And if you think of it, the quantity that changes at that rate is actually the horizontal distance between the corner, between the building and the bottom point of the ladder. And in fact, we already know the value of that, which is 6 feet. So the quantity whose rate of change is known, it's actually, I want to call it the distance, horizontal distance. Distance. And I want to denote it by d. And now the rate of change is the derivative. Again, both these quantities are changing with time, so we think of them as functions of time, and the derivatives of them are rates. So rate of change of height, derivatives are rates of change. So rates of change of height is unknown because that's precisely what the problem was asking about. And the rate of change of distance, like how fast this distance, and this distance by the way is increasing. So how fast it's increasing, it's exactly how fast this point is moving away. And that is 1 foot per minute. So we got these two quantities. Once again, they are not explicitly mentioned in the text, and that's why actually one of them is mentioned. It's 6 feet, but still it's not clear. So once again, one of the quantities is the height of the top point of the ladder, and that as the time goes, so this quantity actually decreases, and we need to determine the rate at which it decreases. So that would be rate of movement of this top point down. And the other quantity is horizontal distance. And as the ladder slides down, this horizontal distance increases. And the rate of increase of this horizontal distance equals exactly the rate of movement of this bottom point, and this the speed of movement of this bottom point, and it's given, it's equal to 1 foot per minute. So these are the two quantities, height and distance. Horizontal distance. Okay, so that's step 1. Now step 2 should be the equation. Step 2, it's relation between these two quantities, which means relation between the height and the distance. Relation or equation between or relating, so connecting the height h and the distance d. So how are they connected? Now if you recall some geometry, so this here is right triangle. And it will be right triangle because this angle is 90 degrees, it's a right angle. So it will be right triangle no matter how the ladder moves. So no matter how, I mean when it slides a little bit, it will be a different right triangle, like this one, like this one. But still it will be right triangle. So every time, at any moment of time, this triangle formed by the wall, the ground, and the ladder, so it will be a right triangle. And since it is right triangle, there is formula, and then the length of the ladder will be the hypotenuse of this right triangle. And the height and the distance will be the two legs. And there is a formula connecting the two legs and the hypotenuse of the right triangle. This is well-known formula, it's the Pythagorean theorem. And this Pythagorean theorem is that the leg squared plus another leg squared equals hypotenuse squared. So in this case it will be h, since this leg height is denoted by h, this other leg distance denoted by d. So what we get is h squared plus d squared equals hypotenuse squared. But since the hypotenuse is the length of the ladder, and that is 10 feet, and then 10 feet squared is of course 100. So this is the relation between the two quantities. h squared plus d squared equals 100. Again, it may be given, but if it's not given in the text of the problem, then you can pull it from some previous knowledge, from some background, like in this case it's from geometry. So h squared plus d squared equals 100. Okay, now what? Now we need to do, so now step 3 should be left hand side derivative equals right hand side derivative. So I guess we don't need this picture anymore, so I will erase it. Step 3. Left hand side derivative equals right hand side derivative. Now this left hand side and right hand side apply to this equation that we obtained in step 2. So this is my left hand side, this is my right hand side. Right hand side is a constant number, it's the length of the ladder squared, and that is just 100, so the derivative of that is 0. So once again, right hand side is a constant, in this case it's 100, so the derivative is 0. Left hand side is more tricky, so it's h squared plus d squared. And so left hand side derivative becomes what? Once again, remember that both h and d are both functions, and so when we do derivative, we have to multiply. We have to do derivative normal way and then multiply times the derivative of that function, which means h squared derivative will be 2h, and then we need to multiply times h prime, and plus, and here we do the same, 2d times d prime. That's the left hand side derivative. And so, since left-hand side derivative equals right-hand side derivative, which is 0, so we ended up 2h squared, 2h times h prime plus 2d times d prime equals 0. And now we need to solve it. One thing I want to do is I want to get rid of those two, just divide everything by 2. And then it will be h prime, h times h prime plus d times d prime equals 0. And now this is the new equation. Like in the previous example, at step 3 we get a new equation that involves both the initial quantities and their derivatives or rates of change. So now we need to plug in everything that we know and hope to find what we don't know. Remember, what we need to know is that h prime. So h prime is unknown, but everything else should be known. Now what exactly is known? Well, d prime, the rate of change of the distance is 1, so this is just 1. What else was known? D was known, it was given, it was 6 feet, because the picture, once again, the picture was like this, and this was 6, this was 10. So this is 1 feet per second, feet per minute, and this distance, this rate is unknown, so that was the picture. So d equals 6. D prime equals 1, h prime is unknown, so I will not put anything for it, it's just unknown. And now, in order to be able to solve for the unknown h prime, so how fast the height changes, that means how fast the top point moves down, well, we need to solve for this, so we cannot have two unknowns in the same equation, so this one should be known. I mean, we should be able to put some number for h. And how can we do that? We don't know the height. So the distance is given, but the height, well, the height should be known as well, because we cannot have two unknowns in the same equation. We won't be able to solve it. So how can we find that height? Well, we can find that height if we go back to the Pythagorean theorem, or back to the equation that we started with, and if we plug in the given distance. So this equation holds for any moment of time. Specifically, it holds at that very moment of time that we are studying. So we plug in d equals 6 in this equation, so we get h squared plus 6 squared equals 100, and that will allow us to solve for h. So it will be 6 squared is 36, so h squared equals 100 minus 36, which happens to be 64, and therefore h equals 8. So h equals square root of 64, therefore it equals 8. Well, often in mathematical problems we need to also consider positive and negative square root. But not right now, we only do positive square root because we're talking about lengths, and lengths cannot be negative. So h equals 8. H equals 8. And therefore we know how to plug, what to plug in here. We plug in 8. And now we have an equation like this: 8 h prime plus 6 times 1 is again 6 equals 0. So h prime, now 8h prime equals negative 6. And finally, h equals negative 6 over 8. Now we can cancel it by 2 and get negative 3/4. That's the answer. So the speed of movement of the top point down, so the top point of this ladder is moving down at the speed of negative 3/4. Why is it negative? Because we're talking about rate of change of the height, And negative rate of change means that the height is decreasing, so height becomes smaller, and that means that the movement is down. I mean, you can see it easily from just from common sense, but if you forgot it, so mathematics tells you. Negative sign here means that the movement is down and not up. And the last thing about units, well, we can do with units exactly the same thing as we previously did. Which means we can plug in units of 6 and 8 and everything. Just remember that it's not just 6, it's 6 times 1, so I want to keep it to 6 times 1. And then plug in all the units and combine them, and this will give us the unit of negative 3/4. So what is 6? 6 is feet, 6 is the distance, feet, 8 is also distance. So 6 is feet. So here I will calculate units, feet times, it was 6 times 1. 1 was feet per second, 1 was the speed, that was feet per second. So feet times feet per second, per minute, feet per minute. And then divided, and here 8 is again distance, and distance again measured in feet. So now this feet will cancel, and what we end up with is feet per minute. So the answer for unit is feet per minute. Negative 3/4 feet per minute. Like I said before, you can actually tell that from common sense. Like, what is this? It's a speed of movement, and speed must be measured in feet per minute. So you can just say that. Or, if you don't like that, then you perform the formal calculation of units, and then you come up with the same, so feet per minute. So the answer is negative 3/4 feet per minute.